Okay, getting toward kind of late in the day, so let's get moving here. You may recall that a year ago we talked about use cases for remote persistent memory, and we talked about a collaboration that we had built with SNIA, where we were going to work together to define, kind of the future of what was needed for APIs to develop remote persistent memory. And I had this slide up there which kind of broke the problem down into a couple of pieces. At the top was this idea that we would start with use cases first to try to describe, what the application requirements were. And from that we would come up with a set of requirements that would drive the API development. And that was something that was being done collaboratively between the OFA and SNIA. And then the work kind of split out a little bit. And on the SNIA side, it was to create and document programming models based on those use cases that we had defined. Those programming models would be in parallel to or an extension to the existing programming model for, the existing NVM programming model and the high availability white paper that accompanies it. On the OFA side, we would take those requirements and go off and develop enhancements to the existing APIs to support remote persistent memory. So what I'm going to give you today is kind of an update on sort of a slow-moving, long-running work in progress, and that's where we are today. So at last year's workshop, there's been a lot of discussion in the industry about low-level technology. A lot of discussion about NVDIMMs, NVDIMMs, and NVDIMPs, and all sorts of different technology and stuff like that. But not all that much discussion about how this stuff is actually going to get applied. There's a big chicken and egg problem going on here. So at last year's workshop, and we're not the first to do this, but certainly at last year's workshop, we began to focus on use cases specifically. And so that discussion about use cases began at the workshop last year, and I'll review that very briefly here. And then it was continued at Flash Memory Summit in August of 2018, and it was developed again at the Persistent Memory Summit in January of this year and continues again today. So the objective here is to define a set of use cases and requirements that can be used to drive an API definition. That's what we're trying to do. One thing I want to point out here, it says at the top, let consumers, if you can read it, because this is just a snapshot of last year's slide, but it says let consumers drive the requirements. But there's a sort of a fundamental difference in the case of remote persistent memory compared to the way we've done this in the past in, say, OFIWIG, when we developed LibFabric in the first place. LibFabric was also consumer-driven, top-down driven, but in that case we had a very clear application that we were targeting, or a number of applications, in particular MPI and SHMEM and some other distributed parallel applications. In this case, those applications don't really exist yet because remote persistent memory is just sort of this emerging idea, so people haven't figured out how they're going to build applications that use it. So we're sort of forced to settle on looking at kind of abstract ideas of what the use cases might look like and use that as a proxy for what we think applications will ultimately look like and try to design APIs that will meet those requirements. That's where we're going here. Last year when I talked about this, I introduced the idea of 3 kind of high-level use cases. Nothing magic about this. There may be 4, there may be 2. We need to define this, refine this thinking quite a bit. But the 3 were a high availability use case, or a data availability if you prefer use case. And this one's been pretty well developed already because SNIA has done a tremendous amount of work in this with the so-called high availability white paper. But there's a couple of others that occurred to me. One was what I called shared persistent memory, and I'll talk a little bit more about what that means. Again, that's a review from last year. And this idea of remote persistent memory, or an extension of the local memory out into the fabric. So really 3 kind of use cases that I wanted to focus on. And again, I'm looking for feedback and input here. Are there more that we've missed yet, or is this sort of a reasonable abstraction of the use cases we should be talking about? I honestly don't know. But I figure if I put something out here that's silly, people will tell me I'm wrong and give me the right answer. So we'll see what happens. We refined this a little bit at the Flash Memory Summit 2018, and we started to describe this idea of consumer requirements and system objectives, because it occurred to us that that was going to influence pretty significantly what the API would ultimately look like. It's a little bit of a roundabout kind of excursion, but I think in the end it will be helpful. So again, this is where that idea was extended at the Persistent Memory Summit just a couple of months ago. we began to discover this idea that use cases really do imply, or the APIs for persistent memory really are implied by, amongst other things, application requirements and system objectives. And persistence is only one of those. And this is sort of something that sort of got stuck in my craw a little bit. You know, we're talking a lot about persistence and how you guarantee persistence and how you do flushes and all that stuff. But it occurs to me that there are other reasons that people deploy the technology which we're referring to generally as persistent memory. For example, you can get tremendous amounts of capacity with a persistent memory device, much more than you can get in local memory. If you don't care about persistence, maybe you just really care about capacity. So I wanted to take a look at other characteristics besides just persistence and see if that tells us a little bit about what these use cases might look like and how that's eventually going to map onto what the API should look like. So we're trying to move the ball a little bit further down the field. This is kind of a stepwise process. It's been going a little bit slow the past year. I expect that progress will pick up pretty significantly from this point forward. But moving the ball a little bit down the field, integrate the various characteristics of RPM, such as persistence, capacity, cost, scalability, a few others like that, into this discussion of use cases and see what that does to our thinking about APIs. I'll warn you right now that I'm not at the point yet of being able to say what I think the APIs are going to look like. I'm holding that back because I really want to understand the use cases first and let that drive our notions about what the API might look like instead of the other way around. No presuppositions, in other words. So this idea about, you know, the characteristic variable, there's others than just persistence. I just talked about this. And the ones that I'm focused on are performance, capacity, and cost. And another one that's a little bit harder to see, but which is local versus remote. And obviously for this room here, we're interested in the remote case, but I think it's worth looking at the local case as well, because the question comes up, can there be a common API that would drive persistent memory regardless of the locality of the memory? And I think my tentative answer is hopefully yes, but probably not. But we'll see how that goes. So if there are, again, other trade-offs that need to be evaluated, please, you know, we need some input here. This is just coming out of my crazy imagination. So if I'm off the wall here, now would be a good time to say so. Okay, this is a picture we're all familiar with, the memory hierarchy. But there's this layer in the middle there, which really isn't, well, we call it persistent memory, but it's not exactly memory, and it's not precisely storage. I hear a lot of people talk about this idea of the convergence of memory and storage, and that kind of sticks in my craw a little bit too, because that implies that the key feature here is persistence, which is one of the characteristics of storage, is that it's persistent. But I'm going to claim that persistent memory really isn't a dessert topping or a floor wax. It's some sort of combination of both of those. So if you look at that memory hierarchy, the little bit finer degree of discernment, if you will, you think of it as three layers. We've always had this notion of a hot memory layer and a cold memory layer. And we now have something that we haven't really had before, which I've described here as kind of warm. And the key point here is that there's really two kinds of warm. It's not like you go from hot to cold and stick warm in the middle. It turns out that there's a gradient there. There's warm, warm, and then there's warm, cool, and then there's warm, cooler, and then there's kind of cold. And it really has to do with locality of reference, local versus remote. No matter what you do, you cannot stop the speed of light. And if you're going to put this stuff at a distance, by definition, it's going to take longer to get to it, no matter what you do. So there's this idea of, you know, we really got multiple layers in that sort of new tier that we've been talking about, which up to now has just been described as persistent memory. And then again, as I've said before, within each of those layers, the sublayers, if you will, there are multiple characteristics that should be looked at: performance, cost, capacity, and maybe some others, as soon as someone pipes up and tells me what those others really need to be. So, you know, again, I'm sort of harping a little bit, but the key drivers here, if we're really trying to select the right technology, it's really going to depend on understanding two things. One is the key design characteristics. What were you trying to accomplish when you built this system? What, you know, were you after scalability? You know, was it a cluster? You know, what was the purpose behind it? And the other is the requirements that are sort of implied by the applications itself. And again, we're prognosticating because there aren't applications yet. So we're kind of guessing what those might look like. A couple of example targets, nothing magic about this. Other people have suggested these. And I've sort of put some stuff at the bottom in order to be a little bit provocative in the hope that people would pipe up and say, you're crazy. That's not right at all. It's not about persistence. It's about capacity or performance or whatever. But these are just examples just to get us thinking. You know, database applications. And again, there's a key question there with the database question. Are you talking about scaling the database on a local node? Or are you talking about building a distributed database, which implies remote persistent memory? Data analytics, graph analytics, they look a lot the same in some regards, not all regards, but in a few. Commercial applications, this is one that kind of got us thinking about this. There have been some interesting presentations by a guy named Scotty Miller from DreamWorks who talked about, you know, what it takes to build a movie with a team of animators. And the problem that they have is right now, any one animator can really only have access to about 8 seconds worth of the movie. So they're very limited in how much progress they can make with their, you know, with their hordes of animators. What they really want is a giant store somewhere that everybody can access at very high rates so that they can work on the whole movie at the same time, not just little tiny pieces of it. There are other examples of that. For example, when you have multiple processes all trying to access a centralized chunk of data for whatever reason. So just a couple of example targets for persistent memory going forward. My favorite, of course, being from Cray, HPC applications. We're interested in scalability. We have problems with things like checkpoints and restarts, things like that. Use cases so far. Let me spend a little bit of time on this one. This was the result of kind of a boiled down and refined result from the think tank that we ran last year at the workshop devoted to remote persistent memory. A bunch of smart people got in the room, started asking ourselves, what would you do with remote persistent memory if you had it? So here are the ones that kind of boiled out of that. Again, this is not a definitive list. I'm looking for input, hoping that people will say, well, that one we don't need to worry about, or you missed one, or three. The first one is, the most obvious one is data availability and protection. This is the one that's driving the current SNIA HA white paper, high availability white paper. The theory is if data is local and it's not written somewhere else, it's not available, it's not protected, it's not availability. So the idea there, what's driving the development of the HA white paper is this idea that you want to be able to replicate local cache to remote persistent memory in order to achieve data availability. So that's one, and I'm going to claim that one's pretty well understood because there's a really nice white paper that came out of the SNIA NVM programming twig that describes that. That's available on the SNIA website, and everybody should go read it. That's been reviewed in OFIWIG. We looked at that and provided some input to it, and that input was accepted, and the white paper was developed accordingly. The next one is what I'm going to call improved uptime or fast restart. So this is one where, for example, checkpoint restart is an interesting one to us in the supercomputer world. If you can't keep a server up more than this long, but it takes this long to checkpoint your data, you're never going to make any progress. So we need to be able to do checkpoints much more quickly than you can do, using standard file or block kind of I/O approaches. The way that's done today is with a technology called burst buffers. Another one would be quick server recovery following power cycle. So if you've got a local memory, a local node, and you've replaced with dynamic memory with persistent memory, then there's some hope that, you know, if that server goes through power cycles, whatever the state of that database, for example, happened to be at the time that you hit your power glitch, will still be there when you come back. Local performance enhancement. Eliminate disk accesses to stored databases. Notice that I did not say replace disks with some kind of persistent memory. What I said is eliminate disk accesses. So this is not about putting an SSD down or an NVMe type of device. This is really about architecting an application such that you don't have to go to disk because you know that you've written the data into persistent memory. And again, the emphasis here is on local system performance. That'll become important in just a moment. Scale-up architectures are ones where you're doing something in an in-memory database environment, but that exceed the capacity of your local DRAM. So this is becoming a problem. I think it's probably a key use case. We've heard lots of presentations in SNIA forums from, for example, SAP HANA about this. How do you build, a data store that's large enough on a local node without breaking the model? The corollary to that is scale-out architectures. any kind of a distributed environment, something that we do a lot in HPC land, or let's say a distributed database kind of environment where the database is actually distributed out in the fabric and is accessible by a number of instances of the database application that are all accessing it in parallel. Next one, disaggregated system architectures. This is my favorite pipe dream. This is the one where you stop thinking about a server as comprising compute, memory, and storage, and you take all those pieces and you just distribute them in the fabric as services accessible to an application. So you allocate resources from that pool to an application. It's sort of like things that are being talked about these days, but not really. It's a bit of a pipe dream, but I think it's worth thinking about. I won't say too much more about that. The basic idea there is that it lets you disaggregate, if you will, or decouple the compute capacity with memory capacity. So you could scale memory capacity independently of compute. If what you need is more memory, you can add more memory in the fabric. You don't need to go buy another server blade and plug it in to get more memory. You just increase the size of the remote memory service on the fabric. And the last one here is shared data. This is the one I alluded to a minute ago with my example about the DreamWorks animation, but there's other examples about it. Basically, it's any time you have multiple processes on independent nodes all trying to access a data store kind of simultaneously. And the last one here is improved disk storage performance, which I've axed out because we're talking here about memory I/O. We're not talking about file or block I/O. So I'm specifically excluding conversation about things like NVMe or anything of that nature. This is about memory accesses, not about file accesses or storage, if you will. The idea here is that there's a difference between the way that data is being accessed. Is it being accessed as a memory operation versus a file or block I/O? That's very distinct from the way that that storage, or that store, if you will, is actually implemented. That's an important point to kind of keep in mind. As far as the applications themselves go, a couple of things that are worth keeping in mind. What is it that the application is trying to perform, or what does it actually need? Does it need performance out of its memory, or does it need capacity? So I already talked about, for example, scale-up databases. There's a little bit of performance in there, sure, but that particular one is more characterized by capacity than performance, probably even more than, say, cost. And again, all of these are subjective at this point, and we need to think much more about what this actually means. But I'm just trying to put these out there as sort of notions to be put into the hopper and thought about. Next is sharing models. So is data shared or unshared? So there's a pool of memory out there. Is that pool or an element of that pool or a region in it being shared by multi-processes that are cooperating to accomplish something? Or is it just an extension of the memory available to a local node or a local process? So shared versus unshared. The memory model, this is an interesting one. I don't really treat it much in these slides at all, but I think it's going to be something we're going to want to talk about. If you're using persistent memory to implement a flat memory model in a target memory node somewhere, that says one thing about what the APIs would look like. On the other hand, if you're building an object store with a persistent memory front end, let's say, or even a back end, that's going to say something very, very different about what the API is going to look like. Characteristic traffic patterns, are you doing small byte transfers or are you doing large bulk transfers? So for example, if you're doing a bunch of very small byte transfers, probably things like byte addressable memory are going to be very, very important to you. But if what you're doing is predominantly large data transfers, you might want to think about implementing that data store using block storage devices with a wrapper around them that makes them look like persistent memory. So there's some others. These aren't exactly use cases, but I think they're going to clearly have an impact on what the API finally looks like. All right, so this is the thing that was sort of the bee in my bonnet. We always talk about persistence, and I'm going to claim that it's not always the case that persistence is required. Again, there are some applications where, gee, if it were persistent, that would be nice, but what I really want is more capacity, or what I really want, is a little bit more performance, or I really want lower cost. But really persistence, if it comes along, that's great, but I'm not counting on it. And again, I'm going to call on my example of my friend from DreamWorks. He said, it's really not about persistence for us. It's really about shared access to large quantities of data. So in some cases, persistence is required, but not required, but nice to have. I just described some of those. In some cases, persistence is actually the characteristic that you're after. And the best example is the high availability case. If you're building a persistent memory device out of devices that are not persistent, you really haven't achieved your data availability goal at all. So we've talked a little bit about some performance, some application characteristics and some system objectives that I think are going to kind of drive the way this thing goes. So just an example, and I've harped on this so I won't spend much time here, but sometimes, but not always, it's the case that persistence comes at a cost of performance. Particularly when we're talking about a fabric, you're talking about the potential for added round trips, for example, things like that. Not always the case, but it's something to be thought about. You can't necessarily substitute. If you're looking at this as memory, and it's just memory that's moved across a wire, you can't necessarily assume that there's no performance impact that goes along with achieving persistence. Capacity, to achieve higher capacity, I mentioned this before, you might want to use a different memory technology. So for example, if you're doing large data transfers, you would probably want to use some kind of a block-based persistent memory device, or in that case, non-volatile memory device, to be careful about the language. First order trade-off, is it local or is it remote? And again, we here in this room, because we're all about fabrics, aren't that interested in the local case, but let me talk about it for just a minute anyway. But sometimes the requirement is met by citing the persistent memory right on the local node. And the best example of that is the scale up case that I gave a minute ago, where you've got a server node and you just want to scale up its memory capacity. So in that case, local persistent memory will be helpful to you because you can put a lot more persistent memory, which is much more dense, much denser than you can DRAM on a server blade. In some cases, whatever you're trying to accomplish is really only accomplished by distributing the system, the persistent memory on a fabric or in a remote way. For example, the sharing case I talked about before, where you have multiple processes on different nodes, that really doesn't make a lot of sense unless that data is on some common remote repository. For example, we're talking about SHMEM, for example, right now, where the memory is on each node. There's some notion emerging about what if you put the SHMEM stores on a remote node and everybody shares them that way as opposed to exchanging data between them. Okay, moving kind of fast here. Excuse me. Of the cases I mentioned before, 1, 2, 3, 4, 5, 6, 7 of them, about 3 of them in my mind sort of fall into local persistent memory use cases. So the one about eliminating disk access, so okay, you wanted to take the rotating media off your server blade and replace it with local memory, persistent memory for some reason or other, because you wanted to eliminate disk accesses, not necessarily change the disk, but eliminate the access. That would obviously be a local case. Scale-up architectures, where I talked about, again, increasing the scale of the memory on a server node, is again a local case, not a remote case. We don't need to treat that one. And likewise, improved uptime and fast restart. The one where we were talking about, if I knew I was writing to local memory that was persistent, I could avoid disk accesses. That's an improved uptime case that's local only. There's another uptime case which is remote, which I'll get to in just a second. So I put a little chart there, and just sort of my thumbnail, finger in the wind idea about which characteristic really mattered for these applications. These are arguable. There's nothing here that's magic. I just wanted to stimulate some thinking. So I would guess if you were doing a scale-up case, for example, you'd be most interested in performance. Probably not that interested in persistence, but if you got it, that would be nice. And cost is probably going to be important. Capacity is probably going to be important for you as well. So just the idea that the particular kind of application that you're using is going to drive the emphasis you have on particular characteristics, which I assert ultimately is going to drive what the definition of the API looks like, which is our goal. Let me shift a little bit to the remote case and put a system model up. I've shown this before. This is not a new picture. This is from last year, as a matter of fact. But the basic idea is that there are processing units on a fabric, and then there's a series of one or more target devices, if you will, or service nodes providing remote persistent memory. These are organized into pools of memory. It could be a shared or unshared resource, and I'll talk about that a little bit more in a second. It can be configured in a number of ways. It could be a flat address model that I described earlier, or an object store model, or some other kind of advanced model for maintaining memory. So all of these are going to have a significant impact on these three characteristics on what the API ultimately looks like for executing accesses over a fabric. So the set of use cases I described before, data availability and protection is obviously a remote case. If you're not replicating data from local cache to some other storage somewhere, that's remote. Improved uptime, I talked about that. That's the HPC checkpoint restart case. I really want to be able to store the state of the machine at periodic intervals somewhere else so I can recover when the thing crashes, which it will. Scale-out architectures, this was pretty obvious, I think, if you're looking at something like a distributed database, and the database scales by adding capacity in memory and by adding processing threads on multiple nodes. That's a scale-out architecture. Disaggregated system architectures, again, Paul's pipe dream. I think there's actually room for this, but we'll see. And then the shared data case that I'd mentioned before. So all of those are remote persistent memory cases. I'm not going to spend a lot of time going through these because, again, these are left over from last year, so you can take a look at them. What's different here is I've tried to put that little table in the upper right-hand corner that describes what I think are the most likely characteristics that typify those particular use cases, whether state availability or checkpoint, which were the two data protection use cases that I had described earlier. In the upper left-hand corner is what such a topology would look like. The lower right-hand corner is kind of a description of how you would use something like this. This one is driving a lot of the discussion that's going on in the IBTA today and a lot of what Tom talked about today about flushes and how all that stuff works. That's really all about data protection. Scale-out use case. The difference here is this is looked at as scalable memory, so you've got a bunch of nodes and you wanted to scale the memory available to each of those nodes independently, so there's no notion of data being shared between processes running on multiple nodes. This is just a pure extension of the memory that's available to you on your local node. So it's purely a scale-out use case. I gave an example here of the usage. Expand on-node memory capacity while taking advantage of persistence. If it's available, it may be useful to you or not. Disaggregate memory from computer. So if you really wanted to scale the system out independently, processing independently from memory, this is one way you would do it. The last use case, the shared data use case, is very similar, except in this case you have multiple processes all accessing data which is commonly shared. And that has implications on locking and being able to force data to persistence. It has implications on things like the difference between persistence and visibility that Tom mentioned before. An important characteristic and something that's actually built into libfabric today is there's this notion of global visibility versus data stored in memory. Okay, getting close here. A couple of preliminary observations, and this is pretty much where I'm going to stop. We're almost at the end of what I have to say here. And again, I'm trying to drive to what the API might ultimately look like. We're not there yet. But one is that some of these non-persistent use cases may not actually require the flush semantics that Tom was describing before. It's not clear, but it's also not clear that those need to be built into the API. Maybe they do, maybe they don't. If they are built in, maybe they are automatic. So in the data protection case, anytime you do a write to cache, for example, you might want that mirrored immediately to a remote memory. That would be an automatic case. There might be manual cases where you say every so often, I'm going to replicate that data or move it for whatever reason. Remote persistent memory, by definition, is NUMA. That's just a warning. Just think about it that way. The remote data is obviously going to be slower access than the local data, even if not by much. We're getting really close, and in the greater scheme of things, it may not be an issue, but I just want to put it out there as something to think about. APIs for local versus remote are likely to be different because of asynchronicity. Again, because there's wire delays built in and round trips, almost certainly accesses to remote persistent memory, and people are free to argue with me, are likely to be asynchronous, where accesses to local memory are almost always synchronous. Capacity use case likely to have different access patterns versus the performance use case. So again, I mentioned this before, are you doing large data writes, data reads, or are you doing small byte accesses? For persistence use cases, there are some that should be automatic. I just mentioned that. and some that are under control of the application, so on demand. You might want to say, I'd like to have this pushed to persistence now. Distinguish between the access method that the client uses, sees, versus the technology that is implemented on the RPM node. I waved my hand about this a minute ago, so be careful to distinguish between, am I doing a file operation or a memory operation? That's the access model, and that's what typifies the difference between a storage operation and a memory operation. Distinguish that from the way that the technology is implemented on the remote node. Don't confuse those. People do that all the time. So I could imagine, for example, a remote persistent memory system that's constructed out of NVMe devices, for example. And I would still call that persistent memory, as long as what's being done, I shouldn't have said NVM, I should have said block devices. That'd be much more accurate. As long as you're doing memory reads and writes, and you're not doing file I/O, block I/O kind of thing, that's what we're talking about here. So the last one, consider the chicken and the egg. Again, I mentioned this in the beginning, there aren't a bunch of applications yet, so it's kind of hard to know what the application requirements are. The reason there aren't a bunch of applications is because the technology is just evolving. So we got this chicken and we got this egg, and I'm not sure which is going to hatch first. Maybe neither. Next steps. I'm going to take all what's included here and what I've sort of been developing in the past year or so at these various conferences and commit it to a document, which I'm hoping will incent people to read and comment on. Let's expand this and fix it, you know, places where I went haywire, and places where I missed something, or in places where it's perfect, whatever. And then once we're at that point, let's begin thinking about what this implies for the API itself. And I think it will sort of fall out. That's my hope anyway. That's what I have to say. Thoughts, comments, suggestions, questions? Michael?
Why would you want to do a block I/O versus a memory access?
I assume you're asking about, yeah, I assume you're asking about why I distinguish between the access method versus the technology. And the answer may be because it's cheaper. I might be able to build a remote memory device out of block devices, which is much more inexpensive than one that's built out of byte addressable devices. If my requirement is for large data accesses, and I'm okay with taking the hit of doing block I/O at the target end, not block I/O at the client end. Others? I knew you couldn't resist, Tom. Thank you.
I just want to mention that the second bullet on your use cases discussed the possibility of fast restart from power, basically. That's what Google is selling today in their SAP HANA solution.
Yeah.
They have a cloud-based PMM solution with SAP.
Yeah.
That might be the pitch.
Anything else?
Yeah, latency. Let's say you were wanting to access your shared memory. Yeah, what kind of latency are you going to expect out of the?
Hopefully low.
Zero.
Yeah, right. Well, you saw that slide about Nirvana, right? It's infinite capacity, infinite persistence, and zero latency. That's what we're shooting for. I don't know. You know, we obviously would like to drive the latency as low as we can, which is why this is built on various flavors of what I'll call RMA technology as opposed to RDMA, where RMA is more general, but it's the same concept. But, you know, it's obviously can't be built on TCP/IP. That makes no sense. Clearly has to be built on an advanced network of some sort. Anything else? Okay, it's almost time for, we got one more session, I think, right?